Okay, so today we're going to talk about the electromagnetic spectrum. Electromagnetic spectrum is the range of all types of electromagnetic radiation. It's like having a spectrum of visible light. There's certain things that are on it. Electromagnetic radiation, I've already taken the liberty of writing the definition, is the movement of energy through space. Um, Pretty much, I got this stock image right here of the electromagnetic spectrum. It's pretty good. But as you see these waves, you'll notice the further right they go, the height stays the same, or the amplitude stays the same, but they oscillate more frequently. That's the frequency of the wave being represented here. And the length has to deal with the peaks. So anyways, um electromagnetic radiation has two things in common no matter which type it is. They all have a frequency and they all travel at the speed of light. And they all have a certain wavelength. And the whole idea of this lesson is we're going to be exposed to the electromagnetic spectrum and we're going to learn how to calculate those things. So, right off the bat, I'm going to give you the constant for the speed of light. It's represented in mathematics and in science with a lowercase c, and it's approximately 3 times 10 to the 8 meters over seconds. And then your frequency is represented by a lowercase v, and this would be 1 over seconds. That's like how you would mathematically compute it. And then you have the actual unit that it's in is hertz, or Hz, but I'm going to leave it as hertz, it's fine. And then your wavelength is represented by the Greek letter lambda, and it's in meters by default, but you can always convert it because of the metric system. Alright, so the other thing I wanted to just kind of gloss over is visible light, since it's on the electromagnetic spectrum and it's the only thing that we can see by default without, instruments. Just like a little information as to how it works. When you have something absorbing red, it'll appear blue, and absorbing orange appear like pretty much if you can go across, that's the color it's going to absorb. That's why when you learn in biology that plants like to absorb light up here with the red and the blue and some purple, they always appear, well, not always, because there's plants that are different colors, but for the most part, anything that does photosynthesis will have some sort of green in it. And that's because that is the light that it's reflecting. It's not absorbing that. And that's why if you shined a green light at a plant, it's not going to be able to do photosynthesis because it does not absorb that light. Pretty much that's how visible light works. And it's somewhat important for chemical reactions because there are certain instruments that we can use. I'm actually trying to build one so we can do it in class, but I don't know if I'm going to be able to do it in time. But if I do, I will definitely show it in class. If not, I'll make a video later when I do it at home. But the idea is I'm going to be able to react some chemicals, and knowing what light is going to be emitted from it, from the reaction, I'll be able to monitor the progress of it and make a graph out of it. It's pretty cool. But anyways, that's why knowing stuff about the electromagnetic spectrum can be kind of important for chemistry. It is used quite a bit. So wavelength is just the physical difference in meters or distance. So let's do that instead of difference. The physical distance, and then in meters, remember that's important, between two successive wave peaks. So essentially it's like the picture I drew up above where I had this, and you have a wavelength here, or you could have a shorter one where it's like, actually, let me do this the cheater way, and if we crunch this, wow, that was an epic fail. This would be also a wavelength. It's not too complicated, but just so you know, wavelength doesn't mean that it has to be far apart. It can be super, super small. All right, so the main formula that this comes from is down here to calculate wavelength and frequency. The speed of light is equal to lambda times frequency. So if you wanted to find out one of these, depending on what you were given, you just divide it out on both sides. So let's do an example. And then I'll give you the formulas for both of these. So actually, let's just do the math proof. It's probably easier. So if you want to, and then I'll label these real quick. V equals freak. So if you wanted to find either one of these, let's say we wanted to find wavelength, you would do wavelength equals C over V, and then frequency would be V equals C over lambda. It's not too complicated, but it's just something that you should know. I mean, if you know this, then you'll be fine, because you can just do the algebra. But anyways, so I'm going to do a quick example or two, and then we will learn about photon energy, and that should be the end of this unit. So let's write this example down. So what is the wavelength for a wave with a frequency of 27.185 megahertz? So if you remember from your conversion sheet, you can use that, I don't care. M is 10 to the 6. So that means that we have 27.185 times 10 to the 6 hertz. So you can just do that to convert. Either way, I don't really care. But that would be how I would do it, because now you can figure out how to solve it. So we're looking for wavelength. If you go back up here, I gave you the formula. So we have lambda equals 3.0 times 10 to the 8 meters over seconds. And then that's times, let me make sure I write this. So that's 1 over seconds. You would have 27.185. Let's put this in parentheses. 10 to the 6, 1 over seconds. So because these are both on the denominator, we can just cancel the seconds out, and then we're going to find meters. So lambda equals, let me open my calculator. All right, so 3.08 divided by, 27.1856. So your answer is going to be approximately 11 meters. And it's really not that hard. You just need to know how to set the formula up and do some conversions. But it's really not too bad. I'm going to do one more, and then we're going to move on to photon energy, and then we'll call it good. Anyways, so A satellite uses a wavelength. Satellite uses a wavelength of 37.5 millimeters. What frequency is it operating at? So, first thing I would advise you to do when you are setting these up is, one, write the formula down. Make your life a whole lot easier. And then two, write down your constant. So, okay. So, we have our formula. We know the length of our wave. We have to convert that to meters because it has to be in meters. Otherwise, you're going to get a wrong answer by about 1,000. All right, so let's see. 37 point times 1 meter over 1,000 millimeters equals 0.0375 meters. So if you're not able to do this in your head yet, the other thing you could do is just write 37.5 millimeters, or 37.5 times 10 to the negative 3 meters. It'll give you the same thing. If you're not able to do these in your head yet, I suggest going back and practicing some conversions. When you're going from meters to millimeters and vice versa, you're really just moving the decimal place 3 places. I just don't want you guys to be wasting a bunch of time doing simple conversions when you could be, solving the problem. Anyways, so now that we have everything we need, we just plug it in the formula. So we have wavelength equals 3.0 times 10 to the 8. If I could write an exponent right, that'd be sweet. Divided by seconds times 0.0375 meters. Wow, I wrote the wrong thing. It should be V. Alright, so now our meters are going to cancel. So we're in frequency because we're in 1 over second. It's not written there, but you have 1 times. And then you have your seconds right there. But, so let's just plug this in the calculator. It's going to be quite a large number. So we have 3.0 E8 divided by 0.0375. And you could do it the other way too. I'll do it both ways and show you that you get the same thing. So 3.8 divided by 37.5 E negative 3. So I hate when my calculator doesn't put it in scientific, but so you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8.0 times 10 to the 9, and then that would be 1 over seconds. So 10 to the 9 is giga, so you're going to have 8.0 gigahertz. So that would be the frequency that wavelength, or that the satellite is operating at. And that's pretty much how you do this. So if you have any questions about this, ask me in class and I'll go over it. But now we're going to focus on calculating photon energy, but I'm going to do that in another video. So I will see you there.